Okay, Nick is next. Nick's in N9 SDF. He's worked at Sound Devices and Amazon. He's currently the Director of Hardware Engineering at Flex Radio, and he's going to talk a little bit about FPGAs, which are a key component of software-defined radios.
I'm definitely tolerant. So, digital logic EU, terror in the FPGA. That's my, I'm my target audience for my jokes. So, I find it. So, what is an FPGA? FPGA stands for Field Programmable Gate Array. And that's actually a holdover from a time when you would make an ASIC and you would lay down base layers and then you leave the metal programmable as a gate array. Nowadays, it's significantly more complicated than that. So it implements what I call timed digital circuits. When you're making a PCB, you can make all sorts of things with digital circuits, but this is a very focused timed digital circuit. And we'll get into that. So many of the FPGA vendors, there are three, well, I guess maybe four major vendors, incorporate several blocks of IP to make these chips really useful across a broad range of applications. So DDR controllers, PCI Express, LVDS SerDes on pads so that you can do all sorts of timing, shifting, and delaying. FIFOs are built in, block RAMs, DSP cells to accelerate math. So it's not just a simple chip, it's not just XOR gates or AND gates. There's a significant amount of technology that goes into these things. So, why do we use an FPGA in SDR? We do. It provides fully deterministic processing. Everything happens at a clock cycle. Every clock cycle, something is happening. There's no interrupts. Processing is fully parallel. So if one multiplier is doing something, any other multiplier can be doing it absolutely in parallel. So it's a fully parallel design. It's fully deterministic. The cost performance can be very high. And you can do a lot of high-end things in high-end processors from Intel, but the cost of entry to those processors is very high. So if you're going to try to make your own board, then you have to have a BIOS, you have to know how to use Intel, and you have to know where to South Bridge. It's an extremely large investment. For something like an FPGA, you get a lot of performance for a fraction of the cost of very high-end signal. Some of the downsides is that it requires a very specific skill set to actually pull this off. And I'll get into some of the things you need to know to actually be successful with an FPGA. It can lead to a somewhat complicated board design depending on everything you're trying to interface to. So whether it's LVDS in order to talk to ADC, or you want to run a SerDes at several gigabits per second. That's all possible with the FPGA, but your board design has to be able to withstand all that, and you have to understand what you're doing to make it work. Usually the pins on the banks require different voltages. If you're going to interface to 2.3 logic, 2.5 volt logic, 2.8 volt logic. And so you have to understand all the complications that come with putting an FPGA down at the board level. Development and debug of digital logic is significantly slower than, I put in quotes, regular software. So, you're able to implement a feature maybe, depending on the size of it, in a week or two, or maybe a day in software. And features like that can take several weeks of test and debug inside an FPGA. It's just a much slower process. So this is sort of my list of, what do you need to know if you want to develop inside an FPGA? Well, you have to know how to make circuits using an RTL language of your choice. There is a push, and there has been for 20 years, to use what's called a C to gates. I can write C code, and then when I turn it into FPGA gates. That's still not the mainstream as far as I know. I think people are still using what's called an RTL, register transfer language, to describe their circuits. You have to know how to use the vendor's tools, whether you're using Altera, now Intel, or Xilinx, now AMD, or Electronics, another the Lattice chips. You have to know how to use their tools, get your design into it, set up all of your files, make sure you set up projects right, and make sure you can get things to compile and work in the tools. You have to understand timing constraints. what those mean, and how to set them up in those tools for those devices, and evaluate them for correctness. If you're going to be using the vendor's IP blocks, you have to know what those are and what does it take to interface to them, both from the electrical standpoint of the pins, but also inside of the IC itself and how you're moving data in and out. I guess this was kind of optional depending on your point of view, but you should know how to simulate your design. Ideally, you're going to make a circuit and you're going to simulate it for correctness. Not everyone who does an FPGA do that. There's a methodology called burn and learn, where they literally burn it into the board, try it out, and go, well, that didn't work. Let's try it, modify it, and burn it in there again. The problem with that is once you get complicated FPGA designs, you are using space inside of the FPGA that you no longer have for debug. So without a true simulation methodology, you run the risk of having problems that are incredibly difficult to find. Simulation can't capture everything, but it can capture almost everything. I should sit with a copy mug and correct me if I'm wrong, or prove me wrong. You need to know how to debug in situ. So if you do have a problem, there are essentially what are called virtual logic analyzers, so you can tap certain nets inside of your design, put it in the board, run it however it's breaking, and get some debug information. That is more of a siren song than anything. Yes, it works. Yes, you can debug with it. Depend on it in a real situation means you could be getting somewhat desperate. You have to make sure that you know how your FPGA will work with external circuitry. So it's going to talk to a bunch of other things. And how's that all going to work? How's it going to work on the board? How's it going to work inside the logic? So there's a significant amount you have to think about to make one of these actually go. And so I wanted to kind of dive into the timing of digital circuits, and then we'll look at a little bit of RTL and how you code some RTL in order to get logic that you want. All right, so this is a very sort of standard and basic description of sort of a timed circuit. There's a clock tree, so these two flip-flops are on the same clock. One flip-flop is launching data from the Q pin that's going through some amount of combinational logic, and then that's being captured at the D pin of the next flop. I'm sure there's at least a couple of people who are thinking, what about an SR flop or a JK flop or a T flop? And we never use those. It's all D flops. Everyone uses D flops. And so the time of flight from the Q output to the D input through that combinational logic, the maximum time of flight allowed is your clock period. If you take too long, and you can actually take too short as well, your circuit will not work as you expect. Too short, the flip-flops will be back to back, but there's a real physical effect of being too short in time. That's like the real thing. So we're going to kind of talk a little bit about this in the next few slides here. So the combinational logic, there are bonus points if anyone can tell me what the circuit is. So it's pretty easy from the screen. The combinational logic, there's no timing there. You're setting the input to an AND gate, OR gate, in this case XOR, and that will ripple through. And so the longest path through this circuit is when you have to transit through 3 gates. So this is important because if you write logic that has 20 different levels of logic that you have to flow to, it will be very difficult to meet a 500 megahertz clock period. So you have to be cognizant as a designer how many levels of logic are you going through. This is essentially a clock diagram that shows what happens if you violate that timing. So you can see the data input. There's the little bubble marked OK is that there's enough time between the rising edge. So the data is stable on the data input for the rising edge. But then it changes with the next cycle right at the next rising edge, hence the yikes. So what happened is this is an interesting phenomenon. You have physically driven the transistors of your flip-flop from being a switch into being a small signal amplifier. So this is bad. We want those things to be switches. Like they should be on or off. There's no middle ground. But what happens in your circuit is you don't know what the voltage is. You know, internally it could be a volt or depending on the part. Like our current Xilinx ones are a volt for the internal logic. Maybe it's half a volt, maybe it's 0.3 of a volt, maybe it's 0.9 of a volt. You don't know. Right now, you've taken those switches and turned them into amplifiers. And so what will happen is, as amplifiers, eventually they will settle. You don't really know how long, you just know that eventually they will. And it could settle high, it could take the blue path, where it says, okay, the amplifier is the gain stage in those transistors, it pulls high. But it could pull low. That is a very real thing. This happens all the time. I have lost months of my life debugging digital ASICs that had this type of error. I think anyone who's done this will have horror stories about this. So if you don't pay attention to this timing, your circuit will fail. It could fail in weird random ways, like the software people come and say, well, you know, we have to write this register value twice sometimes, and we don't really understand why. Or once in a while, this thing just it doesn't work, and we're just not sure. So as a digital designer, you have to understand this and be able to pay attention to these levels of details. So this is kind of my summary, is know thy circuit timing. You don't actually care how many gates or what the propagation time is, mostly. But there are several different ways to violate the timing of a circuit. Sometimes it's bad, and sometimes it's not. It depends on what your circuit is. So you as a designer have to have this knowledge and understand what's going on. Oh yeah, remember that once in a million typically happens over 100 times a second, sometimes 200, sometimes 500. So a once in a million bug, that happens a whole lot of time in your digital logic. The tools can help you with this. So the modern Xilinx tools, some of the ASIC tools, they will help you understand as you're crossing domains, is this a dangerous crossing, is it not? But at the end of the day, a core design can easily defeat what those tools are trying to do, how they're trying to help you. Do not cross clock domains. So carefully ensuring you are safe. This is the #1 source of errors, and they're random errors. So if any of you are going to take a FPGA, the only thing to remember is this: do not cross clock domains without being safe. All right, so now I'm going to go into a few RTL examples just to kind of demonstrate how when you're writing RTL, how is that turning into a circuit? And we'll actually eventually kind of run up to the idea of what's going on inside the FPGA. So as I said, to make your circuit, we're going to use what's called the register transfer level language. The two most common are Verilog and VHDL. They are not the only ones. Those are just some of the very common ones. The code describes the hardware function. You then use the vendor tools to process them and turn them into programming files for the FPGA. Typically it's referred to as synthesis. You're synthesizing a netlist, or you're synthesizing gates. Your code implies the circuit. You are not making a circuit. You are telling the synthesizer what you would like. You are implying. The synthesizer is inferring the circuit. So if you write crazy code and you decide to get out of the 2 rails, you can hit the electric rail, the 3rd rail, and things can go very poorly for you. So that's very important to remember. All right, so this is about as simple as it gets, and this is actually using a variation of Verilog called system Verilog. This is a flip-flop, and this is how you would imply a flip-flop, and the tool would infer the flip-flop. So you're just saying at every positive edge of the clock, transfer the input, the wire in to the wire out. And that's it. That's it for a flip-flop. It gets more complicated, but that's a few very important flip-flop. So this is a flip-flop with an asynchronous reset. This is a common interview question, by the way. How do you do an asynchronous versus synchronous reset? And so for an asynchronous reset, I mean, the code doesn't look very interesting, but the critical part is that in that sensitivity list, the always at, I'm saying, if you see a positive edge of reset, I want you to reset the line. And then we put a conditional around reset. So, because it's asynchronous, the flip-flop itself has to be built to support this. Sometimes they are, sometimes they are not. And finally, this is with synchronous. it looks almost exactly the same, but it's different. And we'll compare the differences here in the next slide. All I've done is remove the 4 cos edge reset. And now I've told the synthesis tool, I want you to reset at the clock. Not whenever reset happens, at the next positive edge of the clock if reset is asserted. So this is, the code that would make that assertion. So again, this is the difference between the two. I mean, I basically changed one thing. I moved one I guess 3 with 4. 3 keywords outside of the sensitivity list, and my circuit is significantly different. So you have to understand that at this level of design, this stuff really matters. You have to know what you're doing and what you want to happen in order for this to happen. So there are a couple of things to pay attention to here. So, some people would say, well, I want the reset to happen asynchronously right away. Like I want as soon as that reset goes. The problem is in your design, you're using, if every reset has this asynchronous reset, there's a timing constraint with this, and you're going to use up resources to reset these flip-flops. And you may not need that, and we could talk more about that. A lot of times in an FPGA, not an ASIC, but an FPGA, it's better, my belief is it's better to have a local reset to your circuit. The routing resources are minimal. You can reset that circuit as you see fit, and it doesn't need to tie into every other flip-flop. All right, so this is an adder circuit. This is not a whole lot of code to generate an adder, right? This is a tiny little bit of code. And this is what you are implying to the synthesizer, that I want basically a full adder structure to go into these 2 flip-flops. That's it. It's very straightforward. So, if we look at this full adder, this is the truth table for it, and on the right are how everything works out, so that some 0 and some 1, which are the bit slices, work out so that you can get 2. If all 3 A, B, and C are high, you're going to get 2 bits on the output. Now, you don't have XOR gates and AND gates and OR gates just floating around, right? You have to do this with another approach. So if you apply a little bit of thought, you think, well, if I had 2 3-bit lookup tables, I could use A, B, and C as an address into the lookup table and just get an entry out to generate 1 bit. And so that's, at the highest level, what happens inside of an FPGA. The tool looks at your logic, it generates a Boolean equation, it crunches it down into these inputs, will transition, and I'm going to use a lookup table in order to generate the outputs based on these inputs. And that's how you're generating the logical functions. You don't have all these gates just floating around hanging out. So this is actually, I'm sure, difficult to read. This is from UG 474 from Xilinx, and this is like the internals of one of their, what they call a slice set, sort of like a super LUT. Like, they put a lot of effort and a lot of engineering into it, so it's significantly more complicated than a couple of little lookup tables. But at the highest level, this is what you need. All right, so I did want to talk a little bit about a state machine. This is how I do state machines. People do them differently. And again, this is using system Verilog. So this is the state definition and clocking logic. And the clocking logic here is very straightforward. At the positive edge of the clock, if my chip select is high, I want you to go to idle. Otherwise, just take in the next state. And so at this point, you have what will turn out to be 3 flip-flops to hold your state, because you have 5 states. If you need 3 flops to hold 5, let that be clear. Yeah. It'll encode down. You can do other things like 1 hot, trade code, and all that stuff. That's an optimization that we aren't going to discuss. So this is how you do the actual combinational logic for a state machine. I'm using special keywords for system Verilog, but at the end, you're saying, if I'm idle, do this section of code. If I'm waiting for the first word, do this section. If it's a read, if it's a write, or if it's a chip select. So this is actually the heart of a SPI. Every job I've been at, the first thing they had to do is write a new SPI interface. So this one's So while I've taken out all of the internal guts, because that doesn't fit on a slide, this is the state machine in order to walk through oversampling is fine. So briefly, to talk about additional topics, like we didn't talk about how to implement safe clock domain crossing. It's its own sort of discussion. How I'm going to use FPGA IP. So the distributed RAM, block RAMs, ASP cells, shift registers. There are high-speed things you can do with the pads. There's macros, all this stuff. There's a lot to talk about there. And this is my last slide. When do things go wrong when you're trying to time your logic? So too many levels of logic for a clock period is very common. It's very common to try to, you're trying to do this, and then I'm going to stuff in a couple more states, or I want a couple of other things, and there's not enough time. If I need to run in 5 nanosecond period, and I've got 15 levels of logic, probably not going to get it. Clock domain crossings that will introduce non-deterministic behaviors. I think I've mentioned clock domains like 17 times. It's a pretty important topic. And poor use of FPGA resources. So, ideally when you're making a design, you want to make it generic, right? Move it wherever, we do whatever. But as an FPGA fills up, you have to start making very intentional choices. I'm going to use a distributed RAM here. I'm just going to use loose logic at this point. I'm going to use a DSP cell here, and I'm trading off the fact that in this design, right now, although I could use this for a different design, but I really need to use this in the moment in order to fit and get it to work. And so this is a trade-off that you're making for every design family in the FPGA. You're choosing to use this logic or this resource because you need it right now. And then, multipliers. So that's it. That's all I have in FPGA design. Thank you.